our third installment for volumes of solids of revolution. So what we've done in the last couple videos is we did something called the disk method. So now this is going to be a slight adjustment or tweak to that. This is called the washer method because the slices look like washers. We'll have one more to go after this, which is cylindrical shells, but that'll be after. We're going to quiz over discs and washers first. Okay, formula. You can notice that before I just had radius squared times the thickness, radius squared dx. Now look, I have r, cap r squared minus lower r squared. So let's talk about what we're seeing here. Well, this would be my low, in this case, x value. This is my high x value, because it's a dx. This is going to be your big radius squared, and this is going to be your little radius squared. What are we talking about? Well, what we're doing is we're finding the volume of washers. Let me draw a washer. Now, in this particular case, it's a dx thickness. So if I don't even worry about a problem, I'm going to draw a washer. So that would be a disc. A disc is solid, like a quarter. A washer has a hole in it. So this would all be solid. And that's empty space right there. That is a washer. And notice, if this is the center, right, this would be my axis of symmetry, then it has a large radius, which we are going to call cap R, big R for big radius. And it has a small radius, which we'll call little r. See, so you have a large radius and a small radius. And this actually makes sense because what we're doing is we're finding the volume of the big disk and we're subtracting away the volume of the little disk, and that would leave us this ring right there, the washer itself. So there's our formula. There's the ideas. Well, I think we should just jump right into an example. Notice we're sticking with our friend square root of x, but notice all I have is two functions here, and that's it. And I'm telling you we're going to rotate it about the x-axis. So let's see how this plays out. I want all the space. First thing we do is we sketch the 2D region. So we have y equals the square root of x. Looks something like that. And y equals 1/2 x has a y-intercept of 0 and the slope less than 1. So we're talking something like this. And if I get rid of this part, do you see the region that's formed right there? I only needed two functions, two equations, because those two form a natural bounded region. So I'm not finding the area. We did that before. That's the area between two curves, and we can do that. What we're going to do is we're going to spin this around the x-axis, and it's going to generate a solid. And we want to find the volume of that solid that's generated. So in your mind, just picture this going around the axis and creating a solid. Okay, now how does that look? Reflect. You kind of reflect stuff. So see the line? I'm going to try to reflect the line about the axis of symmetry here, what I'm revolving it around. Now see the curve? I'm going to try to duplicate that in a reflected sort of way. And then I can kind of do my thing there, although it doesn't help. If you can try to visualize this, this is all solid. And this is all empty space. It's kind of like a vase, except it would fall over, right? If I took a vase and laid it on its side, it's kind of solid. It's got solid glass or stone or whatever. And inside it's empty for you to put the flowers in. The problem is it's got a rounded base, right? If you tried to set it up, it would just fall over. But it's kind of like a vase. So what I want to know is what's the volume, like let's say it was made out of glass. How much glass is there that makes up this vase? The inside of it, that's not glass. It's just this part right here. All right, well, visualizing it is helpful. What I absolutely must do is draw a washer. So how does that look? See the axis of symmetry? I'm going to slice it perpendicular to the axis of symmetry, like this, just like this. So I'm going to go see these. I'm going to draw an ellipse. I should have made that a little thicker. And now I'm going to draw another ellipse inside of that going from the inner boundary here. And that creates a washer. And I'm going to give it a little 3D look by doing this. Notice the thickness right there. That's a dx thickness. My large radius, Rx, is the curve. That's the square root. My small radius is the line. That's this one. Now you don't have to write that on your picture, but you have to see that in your mind. See, if you don't look at the picture, it's very easy to get those reversed, and it gets even worse the deeper we go into this. You need to work through the picture. Given this information, let's try to construct our equation. Well, I erased it, but it is, when you have a washer, when there's a hole in the middle, it's pi times the integral of the big radius, see it? See it's a square root? The big radius squared minus the little radius squared times the thickness, so that's all times the thickness, from my low x, which is obviously 0, to my high x, which I do not know. So I have to find that point of intersection. I could either do that with a calculator or I could do it by hand. This is actually pretty easy to do by hand. So I'm going to find, where do these two curves intersect? This is a little bit of side work. You find a point of intersection by setting them equal to each other. Where does this equal that, right? They equal each other where they meet. So I'm going to square both sides. So x equals 1/4 x squared. I'm going to multiply, and I'll leave it like that. I'm going to move this x over here. 0 is 1/4 x squared minus x. I'm going to factor out an x, so I get x times 1/4 x minus 1. So 1 point of intersection is 0. I already had that one. And the other one is when 1/4 x minus 1 equals 0. Or when x equals 4. Your calculator would tell you the same thing. So that's 4. Let's walk back through that. I drew the square root. I drew the line. And I realized that was my region. I then reflected it so I could see what it looks like when you revolve it around the axis. Then I need to actually look at a washer. So I went perpendicular. It doesn't matter where you go. I always pick kind of in the middle. And I drew the outer, and I made it a little wider so I knew there was an ellipse I had to draw on the inside. I drew my inner one. I gave it a little thickness so I could detect whether it was dx or dy, I made note of what the large radius was and what the small radius was, and then I just started chucking them in my equation. The only part that caused me a little grief is I had to actually compute these limits of integration, the points of intersection. Wasn't too bad, and there it is. Once I get here, the heavy lifting is done. You've done the hard work. The rest, you just punch it in your calculator. I already did that, and I got 8.378, and this is a volume, so units cubed. Now I want to do 2 more examples of this, just like the whole thing from beginning to end. So let's start number 2 here. Example 2. we'll use square root of x again. Y equals 4, x equals 0. Those are my boundaries. And this is about the x-axis. Now this one, I intentionally made it a little weird because I want you to see that if you don't draw it, you just start trying to put stuff in the equation, who knows what you'll do. So let's draw it and see what's happening. I have the square root function. X equals 0 is the y-axis. That's interesting. And this is a horizontal line at 4. Well, look at that. That's this region right here. I think if people weren't careful, they might think it was this one down there. But this is a vertical line, and that's a horizontal line, so that's the region. And what are we reflecting it around? Not the y-axis, the x-axis. So what's that going to look like? I'm going to reflect this curve, and then this line cuts over. And that looks like a trash basket, but the inside, instead of just being cylindrical, actually kind of comes in. So the outside would look like a trash basket, but the inside does look like a vase, like it tapers in, so you can put the flowers in there. So this is all solid here. Here is the axis of symmetry. What does a slice look like? If I slice it here, this is all empty space. This is solid. That is going to be a washer. So I start with the outer edge, and I'm going to draw a little thicker ellipse than I did with the disc method. Excuse me. Excuse me. So there's my inner radius, the smaller part of the circle. I swallowed something wrong. And here is my thickness. That is a dx thickness. I would have to put my ruler down on the x-axis to measure how thick that is. Here is the large radius. Here is the small radius. The small radius is the curve. Now look, no matter where I slice it, that small radius is on that curve. But no matter where I slice it, the large radius stays stuck on this horizontal line. Or in other words, the large radius is always 4 units. It's constant. Interesting. So let's see what the equation looks like. The volume is pi times the integral of the larger radius, which is always 4, so 4 squared, minus the inner radius, which is the function square root x squared, and it is a dx thickness. And since I need my low x is 0, and my high x, I don't know where that is. But I do know that that point is on y equals root x, and I know that y equals 4. So I'm pretty sure x would have to be 16, square both sides. So when x is 16, y would be up at 4 units. So that's 16 right there. There's the setup. And when I punch that in my calculator, I get 402.124 units cubed. All right, that was example 2. We're going to do one more, and we're going to do it from this perspective. See that? I almost said 8 questions out of sheer habit. I'm sure if we were in class, there would definitely be some. Example 3, boundaries. So we're bounded by, example 3, y equals negative 2x plus 4, x equals 4, y equals 4, and we're going to spin it about the y-axis. Right? If you work blind here, You're going to put what you put, and I could almost guarantee you're going to get it wrong if you don't draw it. If you just start putting stuff in the equation. Let us draw it. All right, so this is a negative slope, kind of steep, with a y-intercept of 4. So it's going to look something like this. X equals 4 is a vertical line at 4, so it'll be somewhere around here. Y equals 4 is a horizontal line at 4, so somewhere up here. Actually, I think it's going to be right there. This is Y, and this is the x-axis. So, boy, that got cluttered, didn't it? Here was my first boundary, my second boundary, and my third boundary. And that creates that region. And it's easy to lose track of my x and y axis here. So let's get rid of the stuff we don't need. This should be a vertical line. So we get a triangular region, and it's going to spin around the y-axis. So I'm going to reflect this boundary, and this boundary, and this boundary. Sorry, when I do this to the side, it's hard to get it looking good. Another vase shape, except the inside is straight instead of curved. So that this would all be solid material, and this is empty space. Now in this case, I'm going to cut it perpendicular to the axis of rotation, perpendicular. So let's see what that looks like. Let's try green here. Here's your outer edges. Here's your inner edges. Here's to give it a little visual thickness. Notice how I'd have to put my ruler on the y-axis or read the markings on the y-axis to see that that is a dy thickness. Furthermore, the outer radius goes to this vertical line, and the inner radius goes to the diagonal line. So this is my inner radius, and this is my outer radius. So let's see if we can put the pieces together. I don't need this. The volume of this solid generated is pi times the integral. My outer radius is always, here's the y-axis, this is x equals 4, it's always 4 units. My inner radius tracks along the line that was given. So I want to put minus 2x plus 4 squared, but this is a dy integral, so this has to be y stuff. So I got to take my equation and I got to solve it for x. And that is what I have to put in that slot. 1/2 y plus 2. I can't just put it the way it is because I have to put y stuff in to a dy integral. But it's still based on that equation. Now this has to be my low y value. It's down here somewhere. And this is my high y value, which is up here. So how are we going to find where these intersect? Well, let's see what we can do. What I would do is I would use the equation here. If x is 4, right there, if x is 4, what is y? So if I plug that 4 into there, it'd be y equals minus 8 plus 4. So minus 4, that's 4 down. How do I figure out how high up it is? Well, that one would be where this one chops it off. So that's the y value. So 4 is minus 2x plus 4. If I subtract 4, I get 0 is minus 2x. So I get, that's giving me x equals 0. Oh, duh. It's my bad. It's my high y value. And look at what y equals 4. High y. I was computing, see how this is 0, 4? I was computing the x value, but who cares? We only needed the y value there. So this is from minus 4, which is y equals minus 4, up to y equals plus 4. Yeah, that was a little sloppy. Sorry about that. But that gives me my equation. My volume is pi outer radius squared minus the inner radius squared, but it's got to be in terms of y, not x. This gives me my upper y value. I had to dig for my lower y value by plugging that x in to that equation. And when I plug that in my calculator, I got 268.083 units cubed. All right, you definitely need to play with these. Email me questions if you have them, and I'll be sending you a review with solutions so you can work through that as well. Let me know how it goes.